All right, everybody, happy Friday to all of you. We're going to start today where we ended last time, talking about a really cool example of carbocation rearrangement. Recall that carbocation rearrangement can occur, and where you've been taught to look for it is anytime you have a positive charge on a secondary carbon adjacent to a tertiary or a quaternary carbon. And recall that it involves basically a CH or a carbon-carbon bond leaning over, going sort of halfway through that weird bridged carbonium ion intermediate, and then sliding over completely to make a new bond, and the carbocation shifts to the other carbon. This happens during the pathway of cholesterol biosynthesis. We've already talked about some of the initial steps of that synthesis when we were worrying about biological examples of SN1 reactions. But as you can see here, in biology, we're not limited by carbocation rearrangements solely to make more stable carbocations. In fact, you're going to see that what we're going to do now is going to involve interchange of tertiary carbocations that are approximately similar in stability. And then you're also going to notice that there's lots of other rearrangements that don't occur. And the question is, why aren't those alternatives occurring? One answer could be the enzyme is making it go this way, but that's something of a cop-out. And actually, high-level calculations seem to suggest that what I'm going to show you is the lowest energy pathway. In any case, you have on purple carbon-19, and this is the core structure of what's known as the protosterol cation. Already we have 4 rings fused to each other. Some people lovingly, I suppose, call this 4 rooms or 3 rooms and a bath. I guess the bathroom's the 5-membered ring. I don't really see it, but you may hear people talk about that, and you can just roll your eyes. But this is the classic carbon-carbon bond framework for cholesterol and other steroids derived from it. On carbon-19, you have the positive charge, and on the adjacent carbon, you have this proton that's beta to the positive charge and is highlighted in blue. Now, there are also beta protons here and here, but we don't do carbocation rearrangements here or here because that would give us less stable primary and secondary carbocations, respectively. But you can imagine hydrogen sort of leaning over with its electrons. I didn't really want to delete all that highlighting, but that's okay. The hydrogen leaning over with its electrons, going through sort of a bridged intermediate in which it is sort of equally bonded to 18 and 19, and then if it continues to move towards carbon-19, you now have a new carbon-hydrogen bond between the hydrogen and carbon-19, and that's going to leave a positive charge in the place of where the hydrogen was. One interesting thing is that this 1-2 shift is stereospecific, meaning it occurs in a specific 3-dimensional relationship. The proton literally just leans over on the same face of the molecule. So blue proton used to be down, pointing away from us into the page on carbon-18. It's still pointing in that direction on carbon-19. It's just leaned over. And we're going to have a cascade of leaning protons and methyl groups because now you have this hydrogen on this new beta carbon adjacent to the positive charge. And so again, that hydrogen is going to lean over. We're going to get a bridged carbonium ion intermediate, and then it'll lean over fully to become a new carbon-hydrogen bond. And the stereochemistry of that proton will still be the same. Got a positive charge there. Then we have a methyl group that's now adjacent to the positive charge. And again, we're not going to do a shift of a hydrogen from carbon-13, because that would take a more stable tertiary carbocation and exchange it with a less stable secondary one. The methyl group now can start to lean over with its electrons. We'll pass through an intermediate or transition state carbonium ion like we talked about last time, and then we'll end up with a new bond between the methyl group and now carbon 14, with the methyl group still on the upper face of the molecule as it was before. And now the positive charge is on 15. And then similarly, methyl group in green on carbon 10 can lean over, going through the sort of bridge carbonium ion intermediate or transition state, end up where the positive charge is, and then we will have the positive charge now on carbon 10. And this is actually, in the end, where we want it to be, because the next intermediate in the pathway involves making a double bond between carbons 11 and 10. And if you look at now where the positive charge is, we're set up perfectly for an E1 style elimination, where a base, perhaps from the enzyme or solvent, removes this proton, and electrons from that carbon-hydrogen bond kick down to form a new pi bond. Now, at any stage of that process, you might have asked, why don't we form a double bond there? Why don't we do an E1 reaction from there? You can think of all of these weird potential side products. And I don't have a good answer for why not, other than the cop-out that, well, the enzyme makes it go this way. But remember, enzymes are about speed and kinetics and not necessarily about thermodynamic stability. So it's, again, it's possible that this pathway just happens to be the lowest energy one. Go ahead.
So if you ask us to show the products of an S in one reaction here, would you ask us to draw all of them for each radiochemical, or just a specific one that you want?
Yeah, so the question is, would I ask you to draw all the possible E1 products from all of those possible carbocation intermediates? No, that would be particularly evil of me, and I'm not that evil. For simple molecules, yeah, I'll say draw all the possible E1 products. In this case, I'm just showing you what happens in biology. Yep. Why doesn't the charge continue on to C11 and C6 and so on? Yeah, I mean, you could imagine from this point doing shifts to shift the proton on 11 over, a proton on 6 over, a proton on 7 over. You could even imagine moving these one of these methyl groups. In terms of why it doesn't happen that way, I don't know. It's a good question. When I was first here, now 9.5 years ago, there was a speaker that came through and gave a seminar. He was a computational chemist, and he had actually done some calculations on intermediates in the cholesterol pathway and suggested that the pathway that's been identified goes through the lowest energy structures. So I couldn't tell you why this pathway is the lowest energy, aside from the fact that we're going from one tertiary carbocation to another. But I couldn't tell you why we stop here. It's not totally clear to me. Oh, by the way, it looks like I lost a methyl group on carbon 6. So how about that? All right, E1 style elimination gets you the precursor to cholesterol, which is called linosterol. And already you've got the key features of a lot of cholesterol and steroid hormones. You have the framework of the three 6-membered and one 5-membered ring fused together. You have polar functional groups on this end, and you have non-polar functional groups on this end. So you might expect this molecule to have some what we call amphiphilic character. It might be comfortable in non-polar environments, and this part in polar environments. So you might expect it to be present in membranes, and cholesterol is a major component of membranes. So there's the structure remains very similar, but it's actually sort of 19 different steps to lose 3 methyl groups, this one here and these two reduce one double bond and then move this double bond over here. But you do all of that and then you have cholesterol, which itself is the precursor for a lot of interesting molecules. So this no longer has to do with carbocation rearrangement, but I'm really trying to put a plug in for biological relevance. So I'm going to show you some molecules you might encounter in your future in biochemistry or in medicine as examples of things that come from this same pathway. So the steroid hormones all come through this pathway, and you can notice their structural similarity to cholesterol, and then you can notice the differences. For example, most of these steroid hormones lose this nonpolar tail and replace it with something polar. Estradiol, testosterone, and progesterone all have sort of this similar structure, but it's interesting to note how very subtle structural variations have dramatic effects, right? Up through the C and D rings, estradiol and testosterone are identical. And even in the B ring, the difference is in the A ring. In estradiol, it's benzene with an OH group. In testosterone, it's a enone. And that functional group and shape causes it to bind different receptors and have different biological effects. Progesterone is now, instead of estradiol, it's similar to testosterone in the A, B, and C rings, and the difference is just here in the D ring with a carbon, with a ketone in place of where the OH group is. And then chemists have proceeded to make analogs of a lot of these things. This is an example of a molecule that's used as a, I think, progesterone mimic in contraceptives. And another steroid hormone is cortisol, which is associated with stress. But if you take the OH group and make it a ketone synthetically, you end up with prednisone and or cortisone, which are anti-inflammatories. Some of you, upon injuring various joints, may have had cortisone injections, and the purpose of that is to reduce inflammation. Vitamin D is also, you hear it's a fat-soluble vitamin. This is why, because it comes from nonpolar cholesterol. You take the cholesterol starting material, you expose it to UV light, and the B ring opens up, and you get this strange-looking structure. The chemistry here we won't talk about in 351, but it's really cool. So you should ask your 352 professor about it. But you turn this cholesterol derivative using UV light into vitamin D3, which is why you need to get a little sunlight, but not too much. Finally, another derivative of cholesterol, I mean, it's all over the place, are what are called bile salts. This is how you are able to solubilize fat in your GI tract. Notice that there are plenty of nonpolar functional groups, but this is really fascinating. Look at the molecule and think about what's above the page versus below the page. All right. Above the page, you've got hydrocarbons, methyl groups, CH bonds, other nonpolar functional groups. Below the page, you have OH groups pointing downward. This creates another amphiphilic structure. Think of this molecule like a plate where the top face is greasy and the bottom face doesn't mind being in water. So this acts as a surfactant, or like soap, to solubilize and emulsify fats in your guts. And if a lot of these build up and sort of crystallize out of solution, you can get gallstones, which are beautiful but painful, right? All right, so that's the tour through the steroid world, all because of carbocation rearrangement. Let's see, anything else you want to say about that? Questions? Okay. So we talked last time about, we introduced carbocation rearrangement because it occurs when you try to do an E1 reaction on an alcohol in strong acid. So, and the example of this was this secondary alcohol, which in the presence of strong acid would give you this secondary carbocationic intermediate, which could then do rearrangement to give you this rearranged carbocation, and then you would get E1 products from either of those. Oops, my drawing is not going particularly well. All right, but the question is, what if you wanted just the non-rearranged product? And so we have a method for doing eliminations from alcohols, doing what are called dehydration reactions, because you lose water, without going through a carbocationic intermediate. So I'll show you those reagents now. This involves POCl3, which is phosphorus with 3 Cl groups on it. It looks a lot like PBr3, only the phosphorus is more oxidized and more electron poor. You also need a base, pyridine, and the product is only the desired alkene and no rearranged products. And the reason this doesn't happen is because the reaction first turns OH into a good leaving group, but then the mechanism of elimination is E2. So there's never a carbocation intermediate. Now, I'm not going to draw the mechanism for this in class. It's presented in sufficient detail in your text, and you can look at it there. It's also very similar to the SOCl2 mechanism, so I don't feel like it's worth spending a lot of time on. But notice that this is an alternative strategy if you don't want to do dehydration reactions in strong acid. And there are some other strategies that people use to do dehydration ones, though I think dehydration reactions, though I think this is what we'll stick with for now. All right. Any other questions? Yeah.
So for the stereochemistry with this, are there any inversions?
There's no inversion, in part just because it's an elimination. So what happens is, I'll maybe draw the intermediate. No, I think I'm wrong. There we go. So this is the intermediate. This is now a decent leaving group, but apparently not good enough to leave on its own until the base, pyridine, comes and removes a beta proton. Same rules apply for this E2 elimination, though. If there are alternative beta protons, you have to worry about alternative elimination products, but you don't have to worry about the possibility of carbocation rearrangement. All right. Anything else? Yeah.
Why doesn't the chlorine do the deprotonation?
Why doesn't the chlorine do the deprotonation? The text might show that. I'm not sure. I would say that Cl- is a much weaker base than pyridine, just based on the pKa's of conjugate acids. So what I've drawn is the most reasonable thing. You will find as time goes on, the text will be sloppier and sloppier, and your professors will too, with proton transfers. We will stop carrying in a lot of detail about what the base is. All right. So the last thing we need to do in chapter 9 is to talk about epoxides. And I guess in previous times when I've taught the class, I've sort of delayed epoxides till chapter 10, but we just as well talk about them now. They're in your study guide, and it actually gives us a chance also to talk about how glue works, which epoxy resin works, which is kind of fun. So epoxides break the rule for negatively charged oxygens, or OR minus, being a terrible leaving group. So here's what we mean by an epoxide. This is a 3-membered ring containing compound where one of the atoms is oxygen. Okay? And you might expect, like cyclopropane, there's a lot of ring strain here. And so even though a negatively charged oxygen leaving is a bad leaving group, the ring strain that you relieve if this oxygen were to get attacked totally pays for the negatively charged oxygen being a leaving group. I guess what I'm trying to say is we told you before that we're never going to do a reaction where a nucleophile comes in and does SN2 and OR minus is a leaving group. But because of the 3-membered ring, we can do an SN2 reaction on this particular kind of ether, where the nucleophile attacks from the backside in SN2 fashion, and the negatively charged oxygen leaves. And the reason this is okay is because of relief of ring strain. And then usually in a subsequent step, that oxygen will pick up a proton from somewhere. It's possible that you've got an acidic proton in your reaction mixture. It's also possible that at the end of the reaction, you do what is called aqueous workup, where you add water buffered at some pH, and anything that needs to get protonated at that pH does. And so the final product, when you open up an epoxide in this way, is the alcohol on one carbon and your nucleophile on the other carbon in this sort of 1-2 pattern. Okay, anything you want to ask about that? Do you get the idea that ring strain is relieved when you do this? Go ahead.
I guess my question is, when the nucleophile attacks from the back, it's still on the same plane as the oxygen. I don't understand that very well.
Okay, well, we could show this in a couple of different ways. By analogy, the way I'm showing it now is as though we drew an SN2 starting material like this, and we had the nucleophile approach from directly behind the carbon leaving group bond, and there would be inversion of stereochemistry because the nucleophile had come in from the opposite side. The way I've drawn the epoxide above, each of these bonds is in the plane of the page. So to have the nucleophile approach from behind would probably have it coming in like this, and then the leaving group leaves. But we can draw this process a couple of different ways. If you wanted to, we could draw the epoxide like this. And we could have a nucleophile come in, imagine coming up from below and opening up the epoxide. And then if you did that, let's see, you would have the oxygen up here. The hydrogen would come up on the other carbon, and your nucleophile would be down here.
That makes a lot of sense.
And that may make more sense. It's kind of tough to draw 3-membered rings and stereochemistry, so each of these representations is imperfect, but they'll do. Yeah?
So would there be no inversion of configuration?
There is inversion of configuration, you just can't tell here because it's not a stereo center. Yeah, so if we can make a chiral epoxide, if sure. I'm going to draw an epoxide that is chiral. Alternatively, you could just draw that epoxide this way. And if a nucleophile were to come along and open up the ring, from behind, yeah, the product is going to involve inversion of configuration. That is, the nucleophile is now going to be down. The methyl group, which used to be down, is now up. Okay. So there's not a whole lot new here, except for the fact that the shape is a little bit weird. And we've never before had a molecule where the leaving group is still attached. This is an example of an SN2 reaction where the leaving group does leave, but it's still attached to the molecule. And so products of this reaction have, after we do the aqueous workup and the proton gets removed, the product of this reaction has the OH group and the nucleophile on adjacent carbons, and with that observed stereochemistry. So look out for products that have an alcohol and then something that could have been a nucleophile on adjacent carbons. Look for that 1-2 substitution pattern, because that'll give you a clue as to whether or not you could have made that thing from an epoxide. Generally, in order for the nucleophile to attack directly, that means, and in order for the nucleophile to attack directly and for OR minus to leave, usually the nucleophile has to be one of our good nucleophiles. So that would include things like hydroxide or azide or cyanide or some thiolate or perhaps an acetate or some kind of alkoxide. All of these are good enough to open up the epoxide directly and make the leaving group leave. There's another method you can use to open epoxides, but I'm going to hold off on that for just a minute. One important feature of epoxides, and I can't really stress this enough, is the stereochemical nature of the SN2 reaction allows me to test your understanding of molecular shape and stereochemistry and mechanism really, really well with epoxide problems. So I want you to notice something, and we'll call this that epoxide opening is stereospecific. That means that the stereochemistry of the starting material determines the stereochemistry of the product. So let's look at two different epoxides. And I'm going to try to maybe draw these in the way that might be simpler to see, and I don't like my drawing, so I apologize for that. Let's go. Here's okay. And then let's draw a diastereomer of this epoxide where we put one of those methyl groups going back into the page. I'm just going to point out that the way I've drawn it here is exactly the same as drawing the molecule like this, or as drawing the molecule like that. Okay, you need to be comfortable with both pictures. The relationship between these two epoxides that I have drawn is that they are diastereomers. Right? They're different at one, but not both stereocenters. So let's do an epoxide opening reaction. Let's use OH as our nucleophile. To do OH as the nucleophile, we'll do an SN2 reaction. It doesn't matter which of these two carbons of the epoxide gets attacked because they're identical. We could call this carbon A and carbon B. They're identical by symmetry. The epoxide on top is a meso compound, so it doesn't matter which one gets attacked. Both of them do. We'll draw the mechanism for just one. All right, so let's now draw that product. Here is the O minus that left and then gets protonated later. The OH comes in from the back side, so that means the OH is going to be here. And here are my two methyl groups. First, let's pause and convince yourself that that's the right stereochemistry for this product. Maybe you don't like where I drew my arrow. Okay, anybody want to challenge that, or anybody? I dare you to challenge that. But questions about where we get that stereochemistry from? Yeah.
Maybe I lost it. Where's the alpha hydrogen on
I'm sorry. What?
Yeah, so I lost where he went rather at. Did he leave and go propane?
The hydrogen, no, it's still there. I just didn't draw it. And I should have done. So yeah, my apologies. No, and this is our product. If you want, the intermediate would have looked like this. And then that oxygen would have gotten protonated by water, which is our solvent, and there's a lot more water than there is of our intermediate. And so getting protonated is just a matter of Le Chatelier's principle. All right, I'm going to erase those protons because we can just leave them implied. By the way, is this product chiral? Can you make it the same as its mirror image? Well, the epoxide that started it was a meso compound, but this one is not. Notice if you try to make the plane of symmetry, this one's up and this one's down, so that doesn't work. So this is a chiral epoxide. Can we get a chiral product from a non-chiral starting material? Well, if you do, you have to get both varieties, right? Do you remember how I told you that the OH group could attack carbon B as well? If it does attack carbon B, then we get the other enantiomer. Okay? So that's our first following through the structure of the epoxide and paying attention to what happens to stereochemistry. And we can do the same with the diastereomer down here. I'm going to just make a little bit more space. Oops. Again, in our starting material, we have carbons A and B. A and B are identical in this starting material as well, but not for the same reason. Because actually, if you take a hold of that oxygen and twist the molecule around 180 degrees, this methyl group becomes that methyl group. It has what's called axial or C2 symmetry. Another way of seeing this is if I make an axis that goes down through the oxygen and through that carbon-carbon bond, and I rotate around that axis 180 degrees, A and B are identical, they're actually the same. So in any case, if we have the nucleophile, which is hydroxide, come in from behind and open up the epoxide, we're going to get, and I'm just going to draw the product, I'm not going to show the deprotonated intermediate. The OH will have come in from the bottom face of this epoxide, so it'll have that stereochemistry. The proton will be up and the methyl group will be here. And it may be difficult to see sort of what we're dealing with here, so we're going to rotate around this carbon-carbon bond, bringing this methyl group up towards ourselves to be in the plane of the page. So I'm going to redraw the molecule. And again, if you're struggling with spatial manipulation, spatial reasoning of molecules, this is where you want to work with a model set to convince yourself that I've done this right. If we twist the methyl group down here towards us, that's going to move this hydrogen up above the page and over to this side, and that's going to dip the OH group, which used to be up, down underneath the page. So by opening up the chiral epoxide, either at A or B, we get this other epoxide or this other diastereomer, which happens to be meso. You can see the plane of symmetry that runs right here through the molecule. So the key question is, can you follow the stereochemistry of the starting materials through the mechanism of the reaction, which is an SN2 reaction with backside attack, and follow that through to get the stereochemical consequences in the products? And this is the very definition of a stereospecific reaction. You start out with two molecules that are diastereomers, and then look at our products. Our products are also diastereomers. One other thing I want to point out is each of these products that comes from opening of an epoxide has this 1,2 substitution pattern. All right? These are all 1,2 diols. So there are a lot of ways to write questions of this kind. For example, I could draw a product like this, and I could ask you, where did that come from? What could I have gotten that from? And there are a couple of things you'd have to do. You would first need to recognize that you've got a 1,2 diol substitution pattern, which you could get by opening an epoxide with OH minus. But then, fine, if you're going to do that, what is your epoxide going to look like? What is its stereochemistry going to be? Which way should the phenyl groups be in relation to each other? Can you figure it out? Maybe it may help if we redraw the 1,2 diol in a way that maybe makes the relationship a little bit clearer. Later on, if you want, you can assign R versus S to convince yourself that those two are the same molecule. what then should be the stereochemistry of my epoxide? Go ahead.
Should it be,
You want the meso epoxide? Let's test it. If we have the OH group come in from underneath and the O minus group leave, do we get this stereochemistry? Yeah, looks pretty good. So you need to be able to think through all the stereochemical issues of this reaction forward and backwards. And that's going to take some practice. I wanted to tell you about epoxy glue, but we may have to save that for Monday because there's one more thing we need to deal with. And that is that so far I've shown you how to open up epoxides that have identical carbons. So now we're going to pull that rug out from under you and start dealing with epoxides where the two different carbons are actually different, and we'll have to worry about which one gets the nucleophile. So regioselectivity of epoxide opening. What if you had the following epoxide and you have some nucleophile? I don't really care what it is. Let's have it be a strong nucleophile, Cn minus. Any strong nucleophile. Carbon A and carbon B of the epoxide. Which one do you think does the nucleophile attack? You think it attacks B? Okay, why? Sterics is an SN2 reaction. And so the nucleophile is negatively charged. OR minus is the leaving group. Sterics matter because the nucleophile has to get close before the OR minus group leaves, right? So in that case, yeah, Cn minus will attack the less substituted carbon. So we can draw the product that would come from that. We'll make a new bond between Cn minus and carbon B. Carbon A remains unchanged. The methyl group is still down. The O minus group here gets protonated in a subsequent workup step that we won't show. And then the Cn nucleophile should be down. All right? Nucleophile attacks the less substituted carbon when OR minus is the leaving group. What we mean then is that good nucleophiles are regioselective for the less substituted epoxide. In contrast, you can, under acidic conditions, switch the regioselectivity of the epoxide. So imagine taking the same epoxide starting material and using an acid, using a strong acid, to try to open up the epoxide. First, the first step is that the lone pair electrons on the oxygen would remove a proton from the acid, and then you would get, as an intermediate, this protonated oxonium ion. And what happens next is we observe that Br minus, the nucleophile that's left after we protonate the epoxide, Br minus will attack the more substituted carbon. it's still an SN2 reaction, but it's the more substituted carbon that gets attacked. I'm sorry, I got the wrong stereochemistry there. Br should be down, methyl group is up, OH is up here, proton is down there. Under acidic conditions, you're regioselective for attack at the more substituted carbon. Now, whenever you see a more substituted carbon ending up with some product, what do you think? What do you think an intermediate might be? Carbocation, because more substituted carbocations are more stable. So you might be tempted to think, well, maybe actually once you protonate the epoxide, maybe that OH group just leaves completely and maybe you go through a carbocationic intermediate. That would make sense, at least in terms of which group the OH left from. That's sort of SN1 style reasoning. What's the problem with that? Go ahead. The problem, if you're in acidic solution, what a hydrogen would bond to which one? Sorry. To the carbocation. Okay. You would need, in order to remove a proton from the acid, you would need some nucleophile, and I think the carbocation is pretty electron poor. What do you know about carbocations? Thinking about geometry around now this positively charged carbon A? Planar, which means the nucleophile could come in where? From either side, above or below. And yet, we only observe Br having come in from below. So, how do we explain that? And we explain that by calling this an SN1-like SN2 reaction. What does that mean? Well, reactions can be concerted. That is, they can go through a transition state that involves different levels of bond breaking. And so what we're saying is that in the transition state for this reaction, the bond between carbon and, what's the best way to show this? So imagine a transition state in which the bond between the oxygen that's leaving and carbon A has gotten pretty long. Before the nucleophile starts to, and it's gotten decently long before the nucleophile has started to approach. Okay? We might say that this OH group is mostly left in the sense that the bond is long, but still shields the top face of the molecule from attack. At the same time, in the transition state, there would be a buildup of partial positive charge, and therefore you would want the OH group to leave from the carbon that was more substituted, because the more substituted carbon better tolerates the partial positive charge due to hyperconjugation. What we're saying, again, let me say that again, in the transition state for this reaction, and I'm not really convinced I drew it that well. In the transition state for the reaction, the nucleophile is coming in from behind. The OH group is leaving, but the OH group is already mostly left before the nucleophile starts to come in. That means there's a buildup of positive charge, and the nucleophile will selectively attack the carbon that better tolerates that positive charge. Okay, I tried twice, and I think I botched it. So let me pause for questions, except we're out of time. So we'll start up with that next time, and I'll show you a little bit about how epoxide groups work. This is all still Chapter 9, so I will make Chapter 9 study guide due, I guess, Tuesday, because we haven't finished it up yet.